Hello, this is Dr. Johnson. We're looking at section 2.3 worksheet for Introduction to Statistics. So this section is called Alternative Measures of Strength of Evidence. So again, I've got the split screen here with my worksheet on the right and the reading on the left because there's some similarities here that I wanted to point out to you. So on the left in the reading, you were looking at this idea of this hospital in the UK that had a higher than normal fatalities when it came to heart transplants. And then in the worksheet, we have much more kind of fun and silly research question looking at these two pictures and trying to decide which one is Tim and which one is Bob. So we start off with asking a research question. And so, again, like an example of asking a good research question is in the participation activity there. And then identify the observational units of the study and identify the variable and if it's categorical or quantitative. And so when you're looking at the variable should be kind of like what we're counting up. So imagine if we're making a spreadsheet of all of our class data, which is probably a good thing to do for some of the calculations here. And imagine you've got you basically would put how would you organize your spreadsheet then? And so a spreadsheet has more rows than it does columns. And so you want like rows to be kind of each observation. You want columns to be each variable. And so you want the spreadsheet to be able to work whether or not we sampled like thousands and thousands of people or just our class. And that way, that tells you what's rows and what's columns. So observational units, hopefully we're getting a hang of which ones are observational units, which ones are variables. And then state the null and alternative hypothesis to be tested. So if we look over here, if you look at the null and alternative hypothesis here on the reading, it's stated in regards to the equations and it's restated then in terms of words. And so in this worksheet, you're being asked to express it in words and symbols. So you got to do it twice, just like they did it in the reading here. Okay. So then there's the two photos. You were already asked this question. If you think the face on the left is Bob or Tim, it's basically the same question as the one you're asked in the activity. So hopefully your answer to number 4 is the same as the one you answered in the activity. Okay. So now for number 5, collect the data. So go to our discussion post and see what our class ended up thinking about which one is Bob and which one's Tim. And so since and then we're asking what proportion put Tim's name on the left. We're going to kind of do that. We're making that choice so that we all use the same number. We could have easily have done what proportion put Bob on the left, and that's fine. But we're all going to use the same convention, so we all have the same number. Okay. So, and then by what proportion put Tim on the left, that we're making sure it's a binary variable. Okay. And then we go to our old one proportion applet. There are other applets we will eventually use, but this one's our favorite at the beginning because it's kind of the simplest scenario. So, investigates how surprising the observed class statistic would be if students were just randomly selected, name put in forward. So, we'll use the applet, indicate what you'll enter for the following values: probability of success, sample size, and number of repetitions. So, probability of success would be the number from the null hypothesis. The number of tosses, or would also be like sample size, would be the number of people in our class. Now I'm making this video before there's a class, so I'm going to use made up numbers. So don't use my numbers, you'll get the answer wrong. So I'm going to say 25. Okay, number of repetitions, 1,000 is good, 10,000 is even better. 10,000 might run a little slow if you have an older computer, so you can just use 1,000 if 10,000 is running slow. Definitely don't show the animation. Draw samples. Oh, hide the coins. Come on, get out of here. So, I've got number of tosses. Okay. So then, what am I being asked to do here? What's the next question? Conduct the simulation analysis. Make sure the proportion of heads button is selected in the applet, and not number of heads. So proportion of heads, and then as extreme as. And I'm going to assume that in the class that I'm working with, there was 18 out of 25. So 18 out of 25, which would be 18 out of 25, which would be 0.72. Okay. And so, and then you could use, this should match your hypothesis. So you could have had this or this or this. Okay, actually, as extreme as that, and then you can do two-sided if your hypothesis was, if your alternative hypothesis, if you could use a not equal sign, then you got to do two-sided. But if you did just like greater than, then you would just do one-sided, okay? So I'm just going to do it one-sided for this video. Which is maybe a hint for what your alternative hypothesis should be. All right, so where are we at now? I lost track of where we're at. We're at number 7. So before you so indicate how to calculate the approximate p-value. Count the number of simulated statistics that are equal to, for me, it's going to be 0.72 or higher. Okay, for you, it's going to be a different number. Report the approximate p-value. So my p-value is this number right here. I would report 0.0211. Okay, use the p-value to evaluate the strength of evidence provided by the sample data against the null hypothesis. So remember our chart from last section. So my p-value right here is 0.02, which is in between 0.01 and 0.05. So it's strong evidence. So I would put that into a complete sentence. We have strong evidence that the long-run proportion of students who assign the name Tim to the face on the left is more than 50%. Okay, kind of pulls it all together there. So the p-value is the most common way to evaluate strength of evidence. There's also a very, very similar way, and that is going to be the standardized statistic. So we're going to check the summary stats. So summary stats is right there. Explain why it makes sense that the mean is close to 0.5. Well, you're doing a bunch of coin flips, and so you'd expect the average of all the coin flips to be about 0.5, wouldn't it? So put that into words, in your own words. So explain why it makes sense. Report the standard deviation. So mine is 0.099. You might have a number that's a little bit different. So then report again the observed class values of the statistic. So in my case, my answer is different from yours. P hat is 0.72 because I had, for this imaginary class, I've got 18 out of 25 people saying Tim is on the left. Okay, so then, scoot over so we're there. Calculate how many standard deviations the observed class value of the statistic is from the hypothesized mean of the null distribution. In other words, subtract the 0.5 from the observed value and then divide by standard deviation. So you would get out a calculator. Let's see, I don't think you can see this, but I've got a calculator up on my computer. And so then I would put I would take my number, 0.72, and minus 0.5, and I get 0.22, and then I divide by the standard deviation, 0.099, and I would get, my answer is 2.2 repeating. Yours will be different. Okay, so so then the definition of standardized statistic is basically, we always use the letter Z for a standardized statistic. So this is a thing we do in stats. We reserve different letters for particular things. And so Z is going to be a standardized statistic, which is whenever you have a statistic, which remember a statistic is a number that summarizes our sample. And then, so then you take it, subtract the mean of the null distribution, and you divide by the standard deviation of the null distribution. And so this is the sort of thing you would do if you were changing units, okay? So for instance, if you're changing from Fahrenheit to Celsius, you'd have to do subtraction and then division, okay? Because they're different, they're centered at different places and they're spread out in different ways. So what this basically does is it takes your number, so my statistic was 0.72, and then it takes that 0.72, and then it says how much, when you do subtraction, it's basically saying how much bigger than the null value is that, because that's really getting at more of what's really important there. And then you take that and you divide it by the standard deviation. And so then you say, this basically gives you how many standard deviations are you above or below, so positive or negative. Positive would be standard deviations above the mean. Negative would be standard deviations below the mean. So how many standard deviations are you? And so you're changing your units from just an arbitrary percentage to number of standard deviations, which then kind of, it has a standardizing effect, okay? And so we have a new table for this, for our Z values, our standardized statistics. And this matches pretty closely to the p-values. So between negative 0.5 and 1.5 is little to no evidence. So that's, it follows this bell curve, this normal curve right here. So between negative 0.5 and 1.5, there's little to no evidence because that's what normally happens. Stuff happens in there. If you're in between 1.5 to 2 or between negative 2 and negative 1.5, that's strong evidence. And then if you're that's moderate evidence between negative 1.5, negative 2, and 1.5 and 2. Then if you're past 2 or past negative 2, like that, those sorts of things don't happen that often. And so then you say that's strong evidence. And then past 3, there's hardly anything there. Past negative 3, there's hardly anything there. That's very strong evidence. Okay? So, and then again, these two we'll call statistically significant. Okay? That's the standard way to do it. Okay, so now let's formulate some conclusions. So based on the value of the standardized statistic, so my standardized statistic will be different from yours. Mine was bigger than 2 and less than 3. So I had strong evidence, but not very strong evidence. Okay? And then how closely does your evaluation of strength of evidence based on the standardized statistic compare to your strength of evidence for the p-value? So I've got strong evidence for my standardized statistic because I got 2.22, and I have strong evidence because my p-value is 0.02, which is also strong evidence. So it matches up, it makes sense. Okay. So they're very similar conclusions for both. Now, so now let's see a bit further, look at the scope of inference. We found that in most cases, the observed data provides strong evidence that students do better than random guessing which face is Tim's. That's a hint to which person's actually Tim and which one's actually Bob. All right. In that case, do you think that most students at your school would agree on which face is Tim's? Do you think this means that most people can agree on which face belongs to Tim? Furthermore, does this mean that all people ascribe to the same facial prototyping? So based on the limitations of this study, suggest a new research question that you would investigate next. So basically, like, come up with something else. Use full sentences. Give me some details. Okay. Yeah. So for that one, I'm grading based on if it's actually posing a good question. And okay. So, and then number 11, in exercise 5, you record the proportion of students in your class. You put Tim's name with the photo on the left. Imagine the proportion was actually larger. So these questions, 11 and 12, are going to correspond to your reading, the bottom before the challenge, right here. So in the bottom before the challenge, before this matchup of the 6 steps, these two right here, 4 and 5, correspond to these questions. Okay? And so if you're not quite sure about these, go back to the reading and look at those questions, because it's trying to get at the idea of how the standardized statistic relates to the p-value. So in the standardized statistic, as you get further to the right, the standardized statistic, the p-value is getting smaller. So here my standardized statistic is getting bigger, but my p-value is getting smaller. Okay? And similarly, if I go this way, if I'm way over here, getting away from 0 over here, then my z-value is getting less because it's negative, but it's getting further from 0. So when it's getting further from 0, my p-value is getting smaller. Okay? So use that for answering those final 2 questions. All right, that's it.